Huge thanks to our panelists for sharing all those insights. The next session is a fireside chat on NASA supercomputers and simulating the next generation of robotics. Let's welcome to the stage Anto Patrex, founder and CEO of CosmicBrain AI, and Jason Cornelius, aerospace engineer at NASA. My name is Margarita Geleta. I'm a researcher affiliated with Berkeley AI and Stanford, and I'll be your moderator today. So let's start with some introductions. Jason, tell us a bit more about yourself.
Sure. Well, good afternoon, everyone, or good morning. I don't know where we're at. I know it's right before lunch, but I've had enough coffee, hopefully, for the whole room here, so I think we'll keep it a little bit energized for you guys. So I work at NASA Ames Research Center down in Mountain View, and my background is in aerospace engineering, working on developing kind of machine learning methods to do aerospace vehicle design optimization, and I'll keep it there. I think we'll talk much more about that.
Hi guys, my name is Anto Patrex. I'm the CEO and founder of CosmicBrain AI. I used to work at XAI for a while. Before that, did a couple of projects at NASA as well. Good to be here.
Thank you. So to kick off, we would love to learn more about your work at CosmicBrain AI, Anto. Could you briefly describe your overall approach to training humanoid robots for complex tasks? Also factory robots. I know you have different kinds of robots.
Absolutely. That's a really good question to ask, actually. So as humanity progresses from LLMs, we are getting into this space called physical AI. So I believe the next era of AI is going to be physical intelligence. And one of the biggest problems that we are facing in the world is labor shortages. So if you look at Japan or the Middle East or even the US, there are no workers in the factories. And one of the solutions that we have is to use humanoid robots, right? Right now, the industry is divided into two. We have like legacy robotics companies like ABB, KUKA, Boston Dynamics, and all that. We also have new companies like Figure AI, Optimus, and all that, right? Most of these robots are very pre-programmed and do not have enough intelligence to actually do a diverse set of tasks. And that's where we come in. We are building the brain for these robots so that one robot can actually have 1,000 different skill sets and handle diverse amount of data sets or like environments in one go. So that's what CosmicBrain is doing. Yeah.
And building on that, how do you ensure that those models transfer effectively to real hardware in real planetary conditions?
Absolutely. So there was this breakthrough that happened in January from NVIDIA called Cosmos. So Cosmos, the paper, we believe it's kind of like the attention is all you need paper that enabled OpenAI to build ChatGPT. What the paper did was it combined world foundation models with a physics engine and the digital twin of the robots. So at this point, like in 2025, anyone out there is able to take world foundation models from large amount of video data sets of robots doing different tasks and combine it with actual robot and make it do tasks in the simulation. So what we do is that we take 1,000 hours of real data and convert that into 100,000 hours of model data, right? Synthetic data, which will enable these robots to how to grab an object like an apple and orange in your kitchen counter to doing like complex tasks like in warehouses, packaging, in Amazon warehouses or any factories out there, right? So the physics is advancing as we go. We also have a differential physics engine that is actually powering the simulations for actual real-world robotics as well.
Fantastic. Thank you, Anto. Jason, let's move to you. Your research, your work related to training robots and aircrafts for the Titan moon mission and Mars exploration, oh, that sounds so inspiring. Could you briefly describe your overall approach to training rovers and aircrafts for the Titan moon mission?
Sure, yeah. So we work on a couple different space programs. Obviously, of course, NASA does many, but my group, we've worked very closely with the Ingenuity Mars helicopter, which flew 72 times on Mars in the last few years. And then a lot of what I work on for the last several years is Dragonfly. So this is a fully autonomous helicopter, really a relocatable lander is what we call it. And it's going to be put on a rocket in 2028, launched to Saturn's moon Titan, and then it will operate there for quite a while. And so we use AI and machine learning a lot in kind of how we approach different problems here. And one of them, kind of the specialty that I'm getting into now, is optimizing the aerodynamics and maybe stability and control, or the design of these vehicles using those types of methods. So one of the speakers this morning was kind of talking about different tiers of AI. And there's kind of the classical machine learning, surrogate modeling, which is what we're doing a lot of now. So we have inputs from our simulations that we make a huge database on the NASA supercomputer, and then we can train classical machine learning models to have a relationship between design variable inputs and then the output of performance. And so we're doing a lot of this to kind of accelerate how quickly we can look at thousands or maybe tens of thousands or even millions of design perturbations of the same aircraft, and then come up with the best possible aircraft to achieve the mission that we need to on Titan, for example. And so right now we're doing the same thing for Mars, and basically looking at how we can make a long-range Mars rotorcraft, where we're using the supercomputer. And so we just got 350 new H100 GPUs. So it's a small number compared to some of the things that other folks are talking about here today. But we're having a really nice time using that to advance all the other work that we're doing at NASA.
Do you use similar pipelines for both Mars and Titan?
Similar pipelines? Yeah, they can be quite similar. So I mean, at the end of the day, right, if we're talking about a helicopter or an airplane flying around, the fundamental underlying physics is quite similar. There are some unique peculiarities between the two. So for example, you know, the Martian atmosphere is about 1% the atmospheric density of what we have here around us. So if the air around us is 1.225 kilograms per meter cubed, on Mars it's about 1% of that. On Titan it's about 440%. So the physics though, I mean the Navier-Stokes equations that we're running in our supercomputer calculations, the physics is the same, and then you swap out these numbers. And so the result of this is that you will get different configurations of a helicopter or an airplane or whatever you choose to go with. It will look a little bit different on each of these locations, but at the end of the day, the process that we're using to design them, the pipeline, as you say, is quite similar.
Amazing, thank you both. That was really enlightening. I think now we can explore a couple of common threads on GPU-based acceleration and superclusters for training. Can you share with the audience any best practices from your experience?
Sure. Yeah, so one of the things that I remember from XAI, so XAI had the largest 100,000 superclusters, right? So when handling with a complex models, like video models or simulation models, which takes 10 million hours of data, 20 million hours of video data, right? You need a lot of compute, a lot of like high-end GPUs like H100s or H200s, and you need a massive amount of memory bandwidth, right? So GPU optimization is one of the crucial things when it comes to this. Like, so we have like data parallelization techniques or offloading the load into 100,000 GPUs all at once. So those are some of the techniques that we use to actually distribute the load of the models into a larger cluster. This is better for saving a ton of cost. It saves a ton of power. You don't require as much of power. And also the models are not laggy. So when you have like a lot of GPUs working together, it's prompt in response. So any task that you give the models to actually perform, it's on time, very fast. So these are the things that, yeah.
Any best practices from your side, Jason?
Sure, yeah. So, we use it, I guess, in a little bit of a unique way where actually the really computationally intensive part of what my group does is calculating the actual simulations and physics of modeling these aircraft on the other planets. So for example, if we're going to run what we call a computational fluid dynamics simulation, so we're basically running millions and actually hundreds of millions of calculations, partial differential equations, iteratively on the supercomputer. And so this is really the very expensive part. And so we've been working on this problem for quite a long time. And normally we would use CPUs. So it's very typical to run this kind of problem, one simulation of our aircraft in one flight condition on, say, for example, a few thousand CPU cores. Now, more recently, we've had engineers and computer scientists that are taking these same programs that we use, but then moving them onto the GPUs. Historically, the memory size, the memory limit of the GPUs has been the big constraint there. So it was actually previously a big challenge for us to port those over. But now with the new chips, we're finally getting a large enough memory on board of a single GPU where we can take a pretty large problem and put it on a single one. And so the way we do it now is we parallelize thousands or tens of thousands of perturbations of our vehicle design across all of the different GPUs that we have available, run them all. And then when we do the actual machine learning, now that we have this training data set that we've made, which you can kind of think of it as maybe some synthetic data, right? You've kind of perturbed a massive design space with all of these different potential solutions. And then we use that to train a surrogate model. And since we have the GPUs, we can train hundreds or thousands of surrogates and then pick the best one and use this to do further optimization. So hopefully that kind of answers best practices, at least for what we're doing.
Thank you. Last question. Anto, Jason, what's one lesson you learned about bridging the gap between simulation and reality at such large scale, planetary scale?
Sure, yeah. So, you know, the interesting thing on our side, I would say that I was in school trained as sort of a numerical person. So I was doing these CFD simulations on the supercomputers. And it's funny because then you talk to the experimental folks that at NASA Ames down the road in Mountain View, we have one of the largest wind tunnel facilities in the entire world, actually the largest. And so the folks that run that, they never believe the simulation. The people that run the simulations, they never believe the experiment. And so I've come to the approach where you need a little bit of everything. So even though we have all of this amazing computational resource now, we still need to validate it. And there were some talks earlier today about how you validate the output we get from these models. And I think this will always be a critical step for us to really believe what we find.
Thank you.
So to answer that question, so I do believe that simulations, so you said simulations people do not actually believe in the hardware of the stuff, right? So simulations are definitely the future because we do not have enough real-world data to train the robots as of today. So we need more synthetic data, and that will come from simulations, right? So one of the things that if you look into this world right now, so you might be wondering, hey, why are there no humanoid robots launched as of today, right? Tesla said they will launch Optimus in 2027. Figure AI is coming out with their robots in the next 1 year, mass manufacturing. But as of today, you see robots advancing in hardware, but not much in AI, right? If you ask a robot to do some particular task, it can be kind of really basic. One of the reasons being, for the past 50 years, the robots have been trained in a very legacy manner, right? So a lot of these companies, for training, they use hundreds of different tools. So if you train the robot in a physics engine, you transfer the file to a simulation environment like Omniverse or ISACSIM, right? A lot of data is getting lost in the transfer, right? And that's where a solution needs to take place. We need to build a model that combines physics, world foundation models, and simulations all together with high fidelity, so no data is lost. That is crucial for optimizing tasks or skill sets for these robots and make it happen, right? And we believe this is the gap that is preventing the physical robots into actually coming into your home environments, assisting you with laundry or cooking a food for you or assisting you in your factory floors. So there is a big gap between hardware and software. So in the past 2 years, hardware has gone super big. China has launched backflipping robots and running robots. You can see all over the place. But right now, it's time for us to build the brain and advance it with AI and bridge that gap. So that's where we are at.
Well, we've covered a lot in 15 minutes. Thank you so much, Jason and Anto, for sharing your insights on how NASA supercomputers and simulations are shaping and pushing the planetary exploration.
Thank you.